Hello everyone, welcome to this online lecture. My name is Carl Sommers and I'm going to give a lecture about complex systems approach to economics and finance. I am from the University of Amsterdam. The building of the Faculty of Economics and Business is behind me. So that's the background of this online lecture. And I'm also affiliated with the Bank of Canada, and therefore I should make this disclaimer that the views expressed in this talk are entirely my own views and not those of the Bank of Canada. So I will talk about complex systems in economics, especially in macroeconomics. The title of the talk is Behavioral and Experimental Macroeconomics and Policy Analysis, a Complex Systems Approach. And that's also the title of a recent paper that came out last month, actually, in the Journal of Economic Literature. That is a survey paper about the state of the art of behavioral and experimental macroeconomics. So let me start with a few examples of complex systems. I think you are probably familiar with these kind of examples from different fields. My favorite example is perhaps the swarm of birds here in the top left picture, where all the birds follow some simple rules. They keep a certain range in distance to their neighbors, and the interaction of all these individual rules creates a very nice and complex structure at the aggregate level, a very complex swarm of birds that you can see them in the sky sometimes. I'm sure you see them in Paris as well as in Amsterdam. There are other examples of complex system, the brain, the World Wide Web, but also in the social and economic sciences, a revolution here on the bottom left, an economic crisis here in the middle, and a financial market crisis or crash here at the right. Many different examples of complex systems. Complex systems are applied in many different fields, including economics. So it's difficult to give an exact definition of complex system. There are various definitions in the literature. And what I do here, I just list three important characteristics. Those are three important characteristics, at least from an economic perspective. The first is the interaction of particles, or in economics, the interaction of heterogeneous agents at the micro level. And these interactions create patterns and structure at the aggregate macro level. And that's called the emergent macro behavior. There's a famous paper in Science, an early paper, I think it was in 72 by Anderson under the title More is Different. And that captures the essence of a complex system, that the properties at the aggregate level are more than the properties at the individual level. So that's a characteristic, important characteristic feature of complex systems. The second important feature is that these systems are nonlinear and that there are so-called critical transitions, critical changes in the dynamics. And that means that small changes at the micro level may lead to large and irreversible changes at the macro level. So large changes at the macro level, but also irreversible. They are difficult to get back to the original state of the system. Now, the third characteristic of a complex system is something that is very important in economics. And in complex economic systems, you could say that the particles, the agents in the system, can think. Agents learn and adapt their behavior, and in that way, they change the law of motion of the system. The thinking of the agents is part of the law of motion of the system, and that has to be taken into account. And then there are obvious questions here. If you want to have a theory of the mind, a theory of thinking, That is, how do you model rational or irrational behavior? In particular, how do you model expectations in a complex environment? Okay, so what I will focus on in this talk is a behavioral theory of this kind of model of expectations. And that works by learning of simple heuristics. But these heuristics are not completely free. They are in some sense optimal. So subjects are looking for the best heuristics in a complex, unknown environment. So in this talk, I will focus on very simple models, so-called few type models. Models with only a few type, 1, 2, 3, 4 different types. And we try to match the stylized facts of the economy by these few type models. There is also a large literature of many type models, of agent-based models in economics. So there is a large literature of that. That literature is not covered in my survey, but there is a recent handbook on computational economics, heterogeneous agent modeling. And Jean-Philippe Bouchaud is one of the authors of one of the chapters, and there are many other chapters. There are like more than 15 chapters in this handbook that focuses on agent-based models. So I will not talk about that, but I see that as complementary research. I think both approaches are important. The simple models are important for understanding, and the agent-based models are also very important for understanding and also mimicking and matching more and more stylized facts. So let me start with one of the key features of complex systems, the critical transitions between multiple equilibria and so-called tipping points. Now, there are two plots here. On the left, there is a nonlinear system, but the nonlinearity is weak. So you see here on the vertical axis the state of the system, the long-run state, and here you see a parameter of the system, and you see there is a unique stable state here in this left plot, and that as you change the parameter, the state slowly decreases, and this curve describes the steady state of the system. On the right-hand side, there is a system with strong nonlinearities. And now this curve of steady states has become an S-shaped steady state curve. Okay, so now there is a stable state over here until this point F1, and there is a stable state down here starting at this point F2 and going all the way in the corner here. And there is an unstable steady state in between the points F1 and F2. Okay, so the points F1 and F2 are tipping points, are bifurcation points of the system. When the system is here, let's say this high steady state is the good steady state, when the system is here and you slowly change the parameter, then the steady state slowly goes down until this point F1. And then this steady state disappears as you increase the parameter, and the system jumps to the other steady state. And now you are in the low steady state. Let's call that the bad equilibrium of the system. You are here. And now it's difficult to go back from the bad equilibrium to the good equilibrium. You have to move the parameter all the way here, and the state goes up, but you have to move the parameter beyond the point F2 before the system returns to the good state up here. So this is an important feature of complex systems, a critical transition at tipping points. So this is the plan of the talk. I mentioned the survey that just came out in the Journal of Economic Literature, and that survey focuses on boundedly rational expectations in stylized complex system. Now, it's a long survey, So you can read it if you're interested in this topic. And what I'm going to do, I'm going to focus on 5 points from the survey. There's much more to read in the survey, but these are 5 important behavioral takeaways. The first I already made. I talked about critical transitions and tipping points. This is very important in complex systems, so that's the first takeaway. The next takeaways are the simple forecasting heuristics that make us smart. So the forecasting heuristics are simple, but they are, in a way, they are smart by sort of optimizing the heuristics, optimizing the rule within the class of heuristics. Now, the first model I'm going to show, that is a very simple world where there is only one rule, an AR1 rule, autoregressive of order 1, an AR1 rule, and agents will learn the optimal AR1 rule. That's the first case, first model I will discuss. And then second model with heterogeneous expectations, will be switching between heterogeneous heuristics. And these are anchor and adjustment heuristics. So that's my second model of anchor and adjustment rules. And there the rules can be heterogeneous. Okay, and then one of the main topics of my talk will be laboratory experiments. And I will try to give some empirical validation of expectation rule in laboratory experiments with human subjects. And finally, I will discuss some policy applications, some policy insights, how policy might manage complex economic systems. So this is the plan. I already gave you 1 behavioral takeaway, and I have 4 behavioral takeaways left for the talk. Let's go first to the AR1 rule, AR1 forecasting heuristics, and learning of an optimal AR1 rule. So this goes back to a paper in the Journal of Economic Theory called Behavioral Learning Equilibrium. And what is characteristics about this equilibrium is that it is a so-called misspecification equilibrium. So agents have the wrong law of motion, namely an AR1, but reality is more complex. So it's not the correct representation, it's misspecified. And in a way, this behavioral learning equilibrium is the simplest, maybe most parsimonious misspecification equilibrium that you can think of. So that's why I think it's important. And the idea here is that in a complex economy with many endogenous variables, the perceived law of motion of the agents for each variable is just an AR1 process. They believe that the variables follow an AR1 process. The true law of motion of the system is more complex, but they don't know. They don't know the correctly specified law of motion. So they believe in AR1 processes. That's called the perceived law of motion. But there are 2 consistency requirements. And these are, in fact, fixed points in terms of observable statistics, namely the unconditional mean and the autocorrelation. So a behavioral learning equilibrium requires that the unconditional mean and the autocorrelation of what agents believe of their AR1 rule are the same as the unconditional mean and the autocorrelation of the true actual law of motion. So in terms of the mean and the first order autocorrelation, the beliefs are correct. Okay, and then we introduce a simple learning mechanism to learn the parameters, and that's called sample autocorrelation learning. And in that way, the agents learn the optimal AR1 heuristic. So that's the first theory of AR1 rules. I want to apply this theory in a very simple model. And this is the simple situation you can think of. It's a simple asset pricing model. So think of a stock market with AR1 driving dividends. So PT is the price of the stock. YT are the driving dividends. Dividends follow an AR1 process. And then the market price PT is given by, this is the discounted value. Capital R is 1 plus the interest rate. So this is the discount factor. Discount factor times expected price tomorrow, plus this is expected dividend tomorrow, and that follows an AR1 process. So that's just the AR1 process of dividends, YT. And there is some noise, delta T. So YT are the dividends, and as I said, that follows an AR1 process. So epsilon T is a shock of the AR1 process. I will look at this model, very, very simple stylized, and I refer to the delta T when there is no noise, when delta T is 0, and there is noise when delta T is positive, and then it's IID noise. Okay, in this model, if you apply AR1 rules, you get the following. So now the perceived law of motion is an AR1 process. So that means that agents believe prices follow this AR1. Notice how I write the AR1. Alpha is the long run mean of the AR1. Beta is the first order autocorrelation coefficient. Okay, and the mean comes back here. So that's the 1 period ahead forecast. Alpha is the mean. Beta is the first order autocorrelation. Given this forecasting rule, the actual law of motion becomes, and I use the price equation of the previous slides, I plug in the AR1 rule over here of the price forecast, and this is a 2 period ahead price forecast, because if I go back, this has to be, PT depends on this forecast, so this forecast cannot use PT yet, it uses PT minus 1, and that's why there is a beta squared here. 2 period ahead forecast. The rest of the equations are the same. So this is the model under an AR1 rule. Now let me first say a few words on the rational expectations equilibrium of this model. The rational thing to do here would be to say, well, prices are driven by AR1 dividends. So the simple solution is a price solution where price is a linear function of dividends. And you can show that to have a fixed point under rational expectations, these are the constants that you have to take for the linear mapping of dividends. So rho is the autocorrelation of the dividends. A capital R is 1 plus interest rates. And A is, what was A again? A is a constant here, so it's just determining the equilibrium price, not so important in fact. So that's the rational expectations equilibrium. In particular, when there is no autocorrelation in the shock, so when the rho is 0, this drops out and you simplify to the fundamental price is the mean dividends divided by the interest rate. R minus 1 is the interest rate. An important observation is that under rational expectations, the price is a linear function of dividends, and so has the same properties as the dividends. In particular, the correlation of the rational expectation prices is equal to rho. So the properties of the shocks in the systems under rational expectations are completely preserved in the rational expectation price. That's an important point to make. Now, for this model, you can also compute the behavioral learning equilibrium by imposing these consistency requirements on the mean in the first order autocorrelation coefficient. And what you do, basically, you go back to the price law of motion. I show it again. That's over here. And you compute the mean and you compute the first order autocorrelation coefficient. Everything is linear here, so you can compute these things. the mean and the first order autocorrelation coefficient. And the mean is this expression. And you put that equal to alpha. Alpha is the mean of the AR1 rule. So the mean is correct if this equation is satisfied. For the first order autocorrelation coefficient, without noise, this is the expression of the first order autocorrelation coefficient, and that has to be equal to beta. Okay, so the equilibrium, the BLE equilibrium, is looking for solutions alpha star and beta star, and that's written down here. Alpha star and beta star are the solutions. You can show that there's a solution, and in fact, the mean is just the mean of the rational price. So that means that the AR1 rule is unbiased, and the autocorrelation coefficient is always bigger than this autocorrelation in the dividends. Okay, so that means that we have persistence and volatility amplification. In the model under bounded rationality, we have higher persistence and higher volatility than in the rational case. And this higher persistence and higher volatility is due to this simple misspecification error that the agents are making. Let me emphasize again that the BLE has no free parameters because we have computed the optimal AR1 rule in this setting. Okay, you can make some plots. Here is a plot of the alpha, the mean price as a function of alpha, and the equilibrium is the intersection point here. So the equilibrium is here 1. And here is a plot of the first order autocorrelation as a function of beta, and that's this blue curve here. And you can show that there's a unique fixed point over here. Okay, so these are the solutions, this point and this point. And what is important is that the beta, the persistence parameter, is very close to 1. So it's a near unit roots equilibrium. Okay. But where do these optimal parameters come from? Well, they could come from a learning process by sample autocorrelation learning. And what you do is the sample average is just the average of all past prices, and the first order sample autocorrelation is this formula. Okay, the technical details are not so important here. I just show the formulas. And under learning, the rule, the forecast is given by this equation, an AR1 with time varying parameters. And the law of motion under learning is the same as before, except that alpha and beta are now time varying. And if you look at simulation of learning, now here's again the equilibrium, the same plot. And here is the learning of the parameter alpha. It converges to the mean, which also happens to be 1 here. And here you see the convergence of the persistence parameter. It also converges to something very close to 1. Okay, so under this sample autocorrelation learning, the parameters converge to the equilibrium. Agents learn the optimal AR1 rule. If you look at the simulations of this behavior learning equilibrium, and you compare it to rational expectations, the red curve is rational expectations, the blue curve is the behavior learning equilibrium, and that is much more persistent. You can look at the autocorrelation plots. The rational solution autocorrelation starts at 0.9 and decays exponentially, and the behavior learning equilibrium, persistence decreases very slowly only. Okay, so what do we get? We get an equilibrium where market prices fluctuate around fundamental prices, and the persistence and volatility are much higher, and that's also illustrated in this plot. First, the volatility. So this is the volatility of the price divided by the rational volatility. Here they would be equal, but it is much higher. This is as a function of the autocorrelation in the shocks, in the dividends, and you see excess volatility. Volatility is much higher than under rational expectations. Same is true for the beta coefficient of the behavioral learning equilibrium. This is on the axis is the autocorrelation of the shocks. So that starts at 0, and you see this goes up very quickly. So that's the persistence amplification. For example, when the shocks have an autocorrelation of 0.5, the equilibrium has an autocorrelation already of 0.95. So it quickly becomes a near unit root process. It is also possible that you have more than one equilibrium. Here is an example with a low persistence equilibrium and a high persistence equilibrium. Okay, so that happens easily under this simple equilibrium concept. You can have multiplicity of equilibria. Okay, so you can have behavioral learning equilibria with low and high persistence. On the left, you have an autocorrelation coefficient about 0.3, and on the right, you have the near unit root again. And if you look at the equilibria as a function of rho, so rho is the autocorrelation of the shocks, then you have this S-formed curve. Okay, these are the beta star equilibrium coefficients, and you have the S-shaped curve that I showed to you in the beginning as a characteristic feature of a complex system. Well, here it is. Under this simple equilibrium concept, you have multiple equilibrium. So here is the low persistence equilibrium that is stable. In the middle, there's an unstable equilibrium. And here's the high persistence equilibrium that is stable. It's over here. These are other plots. So that sort of concludes my discussion of behavioral learning equilibrium, of the optimal AR1 rule that agents learn. Now, I applied this idea here into a very simple model, and this asset pricing model driven by dividends, but you can apply this idea easily in more complex, in any macroeconomic or financial model. And that's some of the things we are doing. Tolga Eusen is one of my students who estimates these behavioral learning equilibria, for example, in DSG models, in dynamic stochastic general equilibrium models. And you can do that in very rather complex, like the Smets-Wouters model, where you have 7 endogenous variables and seven exogenous shocks. You can implement this optimal AR1 rule and get then you get results that match the data very nicely. Okay. Let me say now a little bit about experiments, macro experiments. Why would you do macro experiments? I don't know what your background is, but some of you, maybe most of you, must have a physical or a mathematical background, and then maybe you're used to experiments. But in economics, we had experiments in economics, but it was not widely accepted in macroeconomics, because the idea was you cannot build a complex macro economy in a laboratory. But more recently that changed. The last 10 years or so, there are many macro experiments, and I'm going to discuss some of it. And why is it important? Well, this is a saying I learned from my colleagues in experimental economics. If a theory doesn't work in the lab, why would it work in reality? And that not only applies to individual theories, but also to macro theories. So if you have a macro theory, you would like to test a stylized version of it in the lab, see whether it works there. So what is a macro experiment? Well, it is an experiment that studies group behavior. Group behavior in a simple complex systems in the lab. And of course, the aggregate behavior in the group depends on all the individual interactions and decisions. So in a macro experiment, basically you study simultaneously the individual decisions and you study the group behavior, the aggregate effects of those individual decisions. And in particular, I will discuss so-called learning to forecast experiments, where you study individual expectations in a controlled macro system, okay, in a simple expectations feedback system. So basically you take a model with expectations from the theory, you program it, students, subjects are behind computers and they make their forecast decision based on realizations of that model that is programmed in the computer. That's a learning to forecast experiment. And then the key question there is, do agents coordinate? And if so, on what? Perhaps on a rational equilibrium or on something else, a learning outcome, a behavioral learning outcome. Okay, so that's the big question. Under which assumption does the system converge to rational equilibrium maybe? And under which assumption do we get something else? Do we maybe get excess volatility or excess resistance? Here's a quote from a very famous economist, Bob Lucas, Chicago. And that's already a quite old quote in the 80s, in the JPE, Journal of Political Economy in the 80s. And he actually made some kind of advertisement for lab experiments to test learning theories. He says theoretical work is making it clear that there's multiplicity of equilibria. All but few of these equilibria are behaviorally uninteresting. They do not describe behavior that collections of adaptively behaving people would ever hit on. And I think a stability theory, and by that he means a learning theory, can be useful in weeding out these uninteresting equilibria. But to be useful, stability theory must be more than simply a fancy way of saying that one does not want to think about certain equilibria. I prefer to view it as an experimentally testable hypothesis, as a special instance of the adaptive laws that we believe govern all human behavior. So basically, Lucas is saying you should test expectations in the lab. And you should test in the lab whether the learning converges into what. And that's what I will discuss. Here is another quote from another famous economist, John Muth, Econometrica 1961. He was the economist introducing rational expectations. And he says something about heterogeneity. He says, allowing for cross-sectional differences in expectations is a simple matter because their aggregate effect is negligible. Okay, so he says in the aggregate things wash out, but he is cautious. He says, as long as the deviation from the rational forecast for an individual firm is not strongly correlated with those of the others. Modifications are necessary only if the correlation of errors is large. So this is a key point. What is the correlation of errors in a complex system? Does it wash out at the aggregate level or not? Or is there a correlation in the errors? And this is a key point. And you can test that in laboratory experiments. Okay, so this should be tested empirically and in laboratory experiments. Okay, I'm going to show you two experiments, compare two treatments in an experiment. One treatment with negative feedback and one treatment with positive feedback. Okay, so the negative feedback treatment comes from the cobweb model. The price is a linear function of the average forecast of 6 individuals. Okay, and this has negative feedback because when the average forecast goes up, this goes up, and because of this minus sign, price goes down. So that's, for example, a commodity market that is supply driven. When expectations go up, there's more production goes to the market, realized price goes down. That's the negative feedback. Epsilon t is a small noise term here. Then positive feedback. That's the same price equation, but this minus becomes a plus. Okay, so now you have a linear function a linear increasing function of the average forecast of 6 individuals. Now, when the average forecast goes up, the price goes up. So there's positive feedback. These two law of motions have the same equilibrium, which is 60. You can see when everybody forecasts 60, this drops out. You get 60 plus small noise. Same here. When everybody forecasts 60, this drops out. You get 60 plus small noise. So under rational expectations, when the forecast is 60, the price would be the same. The price time series would be the same. The only difference between these linear maps is the slope. The slope is here plus 0.95. So that's like a discount factor in a financial market model. And the slope is here minus 0.95. Okay. Yeah, maybe I should explain that this is positive feedback is typical for a speculative asset market, where when everybody expects a higher price, the demand of the risky asset goes up, so the price goes up. So speculative assets typically have positive expectations feedback. Okay, here are the maps, the linear map with slope minus 0.95. The equilibrium is exactly in the middle here, and the positive feedback map with the slope 0.95 with the same equilibrium, unique rational expectations equilibrium, but it's very difficult to see because the red line is very close to the diagonal. And the problem here is that this system on the right with positive feedback is very close to a system with multiple equilibria, with a continuum of equilibria, in fact. If this coefficient, that is 0.95, if that coefficient would be equal to 1, then the red line would coincide with the blue diagonal, and then you would have a continuum of equilibria. So when the positive feedback is strong, is near unit roots, you are close to self-fulfilling equilibria. So you have these almost self-fulfilling equilibria in strong positive feedback systems. And you can ask yourself whether that will affect the behavior of the individuals. Well, let's see what happens in a lab experiment. And this is negative feedback. This is very stable. And this is positive feedback, which is unstable and fluctuates. The red curve are the prices. These are the individual forecasts, the 6 individuals in the negative feedback. You have heterogeneity in the beginning, and then things coordinate. And here, under positive feedback, you have strong coordination of the individual forecast, but they are coordinated on an oscillation. Okay, so this suggests that in positive feedback, you have coordination on the long non-rational equilibrium price, and you have coordination on an almost self-fulfilling equilibrium. I want to show you some plots of this, some dynamic plots. So what you see here are the blue dots are the 6 forecasts in the first period, and the red dot is the first realized price. And then let's see what happens in the next period. So most of the blue dots jump to this last observation, and because most of them make a high forecast, because of the negative feedback, the realized price is low. The realized price goes here. Notice here is one subject that maybe anticipated negative feedback and made a low forecast. Okay, let's look at the next one and the next one. And already after 4 periods, you see that the forecasts are nicely around the realized price, and the realized price is in fact already very close to 60, the rational equilibrium price. And if you continue, then after 6, 7 periods, the realized price is very close to 60, and the forecasts are also very much coordinated on the price. And this continues and you have a nice stable price behavior under negative feedback. What about positive feedback? The blue dots are the forecast, the red dot is the realized price, is here, and then in the next period, you see that all the dots go here are very close to the price. And in the next periods, they are very close, the forecasts are very close to the price. And they coordinate, but they coordinate not on 60, the equilibrium price, but on, let's say, 37. And when they coordinate on 37, the realized price is 38. And then they go after it, and the price starts moving, follows a trend, and then overshoots the equilibrium. Overshoots the equilibrium, and then mean reverts back to the equilibrium and undershoots the equilibrium. And then, so you see a lot of oscillations here. You see strong coordination under positive feedback. This was just examples of one group, and here are, I think, 7 negative feedback groups. They are all very stable, except for some individual experimentation. And here are the positive feedback groups, 6 of them. Most of them fluctuate substantially. Some of them are more stable. This one, for example, is close to the fundamental. But you have also the possibility of these almost self-fulfilling equilibria. Okay, so what I do now is fit a model to the data. And maybe I should explain this model first and then come back to this positive and negative feedback model. Let me jump a little bit. So this is a behavioral heuristic switching model. We had done a lot of experimental data, different learning to forecast experiments, and we wanted to come up with a model that could explain those experiments. And we came up with a switching model that is related to my work with William Brock. That is called a heuristic switching model. And the paper that fits it to experimental data is the paper with Misha Onufriev. So the idea here is the following. Agents choose from a number of simple forecasting heuristics. Okay. And then there is learning. There is so-called performance-based reinforcement learning. Agents tend to switch to better performing models. That's the learning mechanism. Better rules attract more subjects. Okay. So, and the way to model that is a model for the fractions of beliefs, and they are gradually updated. Okay. So that means that the new fraction of type H in period T is delta times the old fraction, that's the gradual updating, plus 1 minus delta times something that depends on fitness, a discrete choice model. Okay, so the delta parameter is, in the experiment, is something like 80% or even 90%, which means that in 80-90% of the time, the subjects sticks to their strategy and only jumps to another strategy occasionally in 10 to 20% of the time. And how many jump? Well, that depends on the fitness. E to the power beta times the fitness divided by a normalization factor so that all these expressions add up to 1. Okay, so UHT is the fitness measure, and that could be utility or forecasting errors. We take the same measure as the payoff in the experiments, and beta, this beta parameter is the intensity of choice, how quickly agents jump to another strategy, and as I mentioned, delta is the asynchronous updating parameter. So this is a simple heuristic switching model that captures the feature that agents gradually switch to better performing strategies. What are the strategies? Well, we looked in the experimental data. and noted that linear strategies perform very well. So we used simple linear strategies. And in the end, we came up with a model with only 4 strategies that fits the experimental data quite nicely. So let me go through these 4 strategies. The first is adaptive expectations. That takes a weighted average of the last price observation and the last own forecast, with weights roughly 1/3, 2/3. That's the adaptive expectations strategy. Then 2 trend following rules, a weak trend rule and a strong trend rule. And the forecast is the last observation plus a trend coefficient times the last price change. So there's a PT minus 2 here now. And these coefficients, 0.4 and 1.3, were the smallest and the largest coefficient that we estimated in the experimental data. Then rule number 4 is also a trend extrapolating heuristic. There is the price change here on the right, but it has a more sophisticated anchor. This is the anchor, and the anchor is the last price observation averaged with the sample average of all past observations. So I take 50% last observation and 50% sample average. So the sample average can be viewed as a proxy for the equilibrium steady state that might be in the system. So this is a learning, anchor, and adjustment rule. Okay, so these are the 4 rules. This is the switching mechanism. And now I go back to the experimental data. Here is the negative feedback. Here's the positive feedback. The red dots are the experimental data. The green line is the simulation. And you see, it explains very nicely the stable negative feedback prices. On the right, we have the plots of the fractions. And the best strategy here is adaptive expectations, that they start equally, all 4 start equally at 25%, but adaptive expectation dominates. Okay, so why is the negative feedback market stable? Our behavior model says because of coordination on adaptive expectation, which stabilizes the dynamics here. The positive feedback, again, the red are the experimental data points, the green is the simulation, and it tracks very nicely. This is 1 period ahead simulation. So this simulation uses the same information as the subjects in the experiment have. So that's 1 period ahead simulation. And if you look at the strategies, they start out equally 25%. And now what happens is that the strong trend following strategy is the blue one, dominates and goes to almost 80% of the market after 15, 20 periods. Why? Because there's a strong trend. Trend following works well, so subjects switch to trend following behavior that dominates the market for a long time until the end when the weak trend starts increasing its share and the strong trend rule goes down because the trends are less strong here at the end than they were in the beginning. Okay, so what is our behavioral story? Our behavioral story is trend followers amplify fluctuations in positive feedback systems. And this is a very stylized model, stylized experiment, but there is already an idea for a policy implication, namely to stabilize the system. Maybe you should add some negative feedback to stabilize the trend following. That's an idea for policy that we will explore later. So this behavioral heuristic switching model fits the negative and the positive feedback experiments quite nicely. Okay, one possible critique on this model could be, where do these rules come from? Where do these coefficients of these rules come from? And I said they were estimated from experimental data, but the model, these rules use then information of the experiment. So you can, the coefficients, it's not clear why subjects would start using the coefficients of these rules. So the next model will generalize that and will provide some evidence how subjects may learn the coefficients of the heuristics. So this is a genetic algorithm model with a smart heuristic, what we call a smart heuristic. And the idea here is that agents learn two parameters of a linear heuristic. And that's an anchor and adjustment rule that is written down here in this equation. So this is the forecast by individual I using parameters h of rule h at time t. And the rule is really an anchor, that's the first two terms, is an anchor and an adjustment. Now the adjustment is easy. The adjustment is again a trend parameter times the price change as before. But the anchor is not just the last price, but it's a weighted average of the last price and the last forecast, the last own forecast. So the weights given to last price and own forecast are alpha and 1 minus alpha. And the trend coefficient is the beta. So here you have your two parameter rules, and now agents try to learn these two parameters. Okay, so you start with initial intervals, and also we should say that the rule contains many or several simple rules as special cases, naive expectations, adaptive expectations, trend following expectations, all by choosing the appropriate coefficient. Naive expectations, for example, beta is 0, alpha is 1, then you have naive expectations, and so on. So these simple examples are nested within these anchor and adjustment rules. Also the rational rule is nested, namely alpha and beta are 0, and then this forecast should be the fundamental price. Then you have the rational rule. So that's also nested as a special case. Subjects learn these coefficients by a genetic algorithm. Now, I don't want to go through the details of how this GA exactly works, but the idea is the idea of survival of the fittest. The probabilities of selecting a rule depend on the performance, the forecasting performance of that rule. And in each step, there is reproduction of new rules. Okay, so there are parent rules that produce new rules, that's the reproduction. There is some mutation going on. And there's also something called election, an election operator, and that is maybe typical in economics for the GAs in economics. New rules are only admitted to the population if they do better than previous rules, or if they do better than rules that are already used in the population. Okay, so you have the new rules have to be better to be admitted to the population. So that's a sort of an element of rationality in this GA selection. Okay, so that's the genetic algorithm. And now let's look at some experimental data. Now here are the experimental data are at the top. This is negative feedback and this is positive feedback. Now it is slightly different from the negative feedback experiments I discussed before, because there is a big shock here. Okay, there's a shock to the equilibrium, a permanent shock to the equilibrium level. One shock here and one shock here, shock to the equilibrium level. And what you see in the experiments is that under negative feedback, the 6 agents quickly learn. Then comes the big shock, then there is some disturbance and there is some oscillations, but then they quickly learn the new equilibrium. And then there's another big shock, and then they quickly learn the new equilibrium over here. Okay, so that's the experiment under negative feedback. And you see the GA model does very nicely. Here is a GA model. The black curve is the price, and the green curves are the 6 GA agents. And this looks very similar to the experimental data. This is a 65 period ahead GA simulation. So it works quite nicely. Same for positive feedback. These are the experimental data. You see quick coordination of the individuals on the price trends. The price oscillates. Here comes the big shock. But subjects are not told about the shock, only that they can occur, but they are not informed about the shock. And almost nothing happens under positive feedback. And then slowly the system moves down to the new equilibrium, but then undershoots it here. And here comes again a big shock, but only slowly the price adapts and then overshoots it and oscillates. Okay, and the GA model, here is an example of a GA simulation, is again very simple. So the GA model mimics well both the negative feedback and the positive feedback experimental data. So here are some Monte Carlo simulations of negative feedback of the mean. The mean, that's the top plots, and the standard deviation, those are the bottom plots. Let's look at the mean first. The blue curves are is the 90% confidence interval, the blue line. So you see the red line is the mean, and you see the mean is very close to the experimental data, and actually the standard deviation of the simulation is very small. Okay, here for positive feedback, the mean is the red curve. Okay, the blue ones are again the 90% confidence interval, and almost all of the experimental data, the pluses, are inside the confidence bands of this GA simulation. Here is the standard deviation of the individual predictions, and you see standard deviation goes down, there's coordination, standard deviation goes down, and then sort of becomes constant, and now comes the big shock. Standard deviation of the forecast goes up, and then gradually goes down again, okay, and stays sort of at this level, then goes up again, and once more it goes down. So in the negative feedback, the big shocks lead to a big heterogeneity in the forecasting behavior, but then quickly the heterogeneity decreases again, and we go back to coordination on the new equilibrium price. Situation on the positive feedback is different. The heterogeneity is in the beginning high, it goes down very quickly. In fact, it goes down even quicker than here. So the coordination here in positive feedback is very quick, but it is typically on the wrong equilibrium price. And then it stays there, it stays coordinated. And in fact, the big shocks, the big unanticipated shocks hardly have an effect on the heterogeneity in the individual predictions. So what are these alpha and beta parameters then? What does the GA model tell us about the parameters? These plots on the left are the negative feedback. Alpha is at the top, beta is at the bottom. First of all, the beta, the autocorrelation coefficient, it converges to 0. Okay, so agents learn a rule with almost 0 autocorrelation in negative feedback systems. The alpha starts around 0.5 and then goes up to 0.7, but basically goes back to something like 0.6, 0.55. So something like 50%. That's different on the positive feedback. the anchor under positive feedback, the weight goes almost to 1, to 0.95. So a lot of weight is given to the last observation on the positive feedback in this anchor and adjustment rule. And the trend rule is clearly positive. The trend coefficient that subjects learn is positive, and it goes up to 0.8, 0.9 even in the long run. Okay, so here is the summary. The average heuristics under negative feedback, agents learn to use adaptive expectations with coefficients of about 50-50. That's the most popular rule in negative feedback. And under positive feedback, agents learn to become trend follower. And the trend following rule gives almost all weight to the last price observation and has a trend parameter of 0.9. So that's where these coefficients come from, by selection of better performing rules. Okay, I come to the last topic of my lecture, the last behavioral insight. What does this mean for policy? How can you manage complex systems? Here are some lab experiments that show big bubbles. And the blue curves, these are asset market experiments. They show very big bubbles. We've done that with groups of 6. We've done it with groups of 25 to 30. And the big bubbles are very persistent. And that is probably due to the positive feedback. Positive feedback causes instability. How could one stabilize these big bubbles? We even did very large groups. This is an experiment in a recent paper that is coming out or has been published in Experimental Economics, that compares groups of 6 to groups of 100. And also in the groups of 100, we have these large bubbles and crashes. So the red curve is the price. The black curves are the individual forecasts. There's strong coordination on a bubble, and then there's a crash. Same in small groups. Okay. So what I want to present at the end is a housing market experiment with positive and negative feedback, and where we play a little bit with the strength of the positive and the negative feedback. And the idea here is that the housing market depends on the supply of housing, and housing market depends on the speculation due to increasing housing prices. Okay, so the housing price is now the discounted value of the expected price tomorrow if there is no supply of housing. If C is 0, this is just an asset pricing model with a discount factor of 0.95 that has these very large bubbles. Okay, but if you have housing supply, then the parameter C increases. And the intuition, now the behavioral intuition, is that an increase in housing supply, that is an increase in the parameter C, adds negative feedback to the system, and that weakens the overall positive feedback. In fact, the eigenvalue of this system is 1 minus C divided by 1 plus R. Here's the eigenvalue. That eigenvalue, when C is 0, it's 0.95, the discount factor. And when C increases, that eigenvalue goes down. And so you weaken the positive feedback. And now we can run different treatments with different parameter C with an eigenvalue of 0.95, an eigenvalue of 0.85, and an eigenvalue of 0.7. And with the near-human root, you have these large bubbles and crashes. When the eigenvalue is 0.85, you have oscillations, but no stable equilibrium yet. But when it's 0.71, actually the price converges to the rational expectation price. So indeed, in these simple stylized experiments, you see that adding negative feedback stabilizes complex positive feedback systems. Okay, so that behavioral intuition seems to work. Here are some more plots. again, the three treatments: strong positive feedback, large bubble, and here are the simulations of the same heuristic switching model that I discussed before. And you see, it's the strong trend rule number 3 that dominates the behavior, because there is a strong trend and a strong bubble. Trend following dominates, and that causes the instability. When the market oscillates, in the beginning it's the strong trend rule because there's a strong trend here. But then after 15 periods, rule number 4, the learning anchor and adjustment rule, dominates. So why does this market oscillate? Because of coordination on the learning anchor and adjustment rule. And finally, in the stable case, in the beginning, the trend rule dominates here, and then the learning anchor and adjustment rule in the middle, and the market oscillates. But at the end, adaptive expectation dominates. Adaptive expectation was the worst rule in the beginning, but starts taking off in period 35, starts dominating and stabilizes the market. These are similar plots, just averages over all treatments, but the plots are the same. And what is important is the policy implication. Negative feedback policies that weaken the overall positive feedback may stabilize markets by preventing coordination on trend following behavior. That's the key point. How do you manage behavior? Well, if the positive feedback is weak, then trend following is not a good strategy. And that was a destabilizing factor in those markets. So that's how you can manage a trend following behavior. Okay, I come to my conclusions. Let me start with the 5 behavioral takeaways. Complex systems, and those are systems that are nonlinear, often they are heterogeneous. They exhibit critical transitions between multiple equilibria. We have seen several examples of that. One simple theory of learning is just an adaptive learning of an optimal AR1 rule. So you learn the mean and you learn the persistence coefficient, and that generates near unit root prices, excess volatility, and persistence amplification. Then we have seen a parsimonious heterogeneous expectation switching model based on relative performance. And these heuristic switching between anchor and adjustment rules fits experimental data well. They also fit empirical time series data well. I did not discuss that, but the survey also discusses the empirical literature in that sense, and you get a good fit there as well. Negative feedback policies can affect the self-organization process and can prevent coordination on trend following behavior and stabilize complex markets. So that shows the important thing for policy, which is add negative feedback to the system. There are many open questions. We discussed an optimal AR1 rule, but I think you would like to go to an AR2 to allow for trend extrapolation in the adaptive learning model. That is, I think, an important extra parameter that also allows for the possibility of complex eigenvalues, and that's could be very relevant for when you have cycles, boom and bust cycles in the model. Homogeneous versus heterogeneous expectations. You can do both approaches. It probably depends on the application, and you can try with a simple homogeneous rule for all agents when the fluctuations are not too strong. But when you have bubbles and crashes, bubble and crash dynamics, then probably a heterogeneous expectation model is more flexible because it can quickly switch to a bubble and quickly go back to a mean reverting fundamental rule. I think all this is not only theoretically and empirically interesting and important, but I think it's also important for policy. And in general, what you would like to do, you would like to be able to say something about optimal policy under simple behavioral forecasting heuristics. Okay, that concludes my talk, my presentation. If you want to know more about the details, you can have a look at my gel paper, or you can start working on this topic yourself. Thank you very much for your attention.